So today we have the pleasure to have Ruth. She did her bachelor degree in Harvard, had PhD in a postdoc in Harvard, then she became a lecturer in Harvard, joined Santa Barbara as an assistant professor, and joined Santa Cruz. She became the first holder of the E.K. Gunderson Family Chair in Theoretical Astrophysics at UC Santa Cruz. She won many prizes, including the Helen B. Warner Prize for Astronomy, and there was a broad range of physical processes in planetary systems, including the evolution of planetary disks, planet formation, gravitational dynamics, and the evolution of atmospheres. And today she will tell us about blowing in the wind, atmospheric escape, debris disks, structure, and planetary hazes. So, Ruth.
Everybody, I'm going to be talking today about a few possible observational consequences of the interactions between stellar winds and radiation pressure planetary systems. I'll talk about all three of them, but if people are chatty, I'll just talk about two of them. So feel free to be chatty. All right. So as we know, planets and planetary systems exist in an environment produced by their star, high energy radiation, stellar winds, radiation pressure, all of these things impact planetary systems. And that's the theme that I'm going to be talking about today, but I'm going to be talking about this in a few different contexts. So the first one is the atmospheric escape from planets. This is something I've been interested in for a long time. And I'm going to be talking about it in the context of the stellar wind, but just to give a little bit of context, I'm going to give a little bit of background and tell you some things that we've been working on in my group in this area. So as you probably know, in the exoplanet population, so here's planet size and orbital period. If you look at the sub-Neptune and super-Earth population, so here's two Earth radii here, we can see that there's a bimodal distribution of planets. And this gap here is interpreted to be the result of atmospheric loss. And this is actually one of the few nice observational features that actually was predicted by theorists, not by me, but by theorists. So we just have to appreciate that. So Lopez and Fortney and Owen and Wu both predicted that this feature would exist before it was observed on the basis of photoevaporative mass loss. And the reason for that is that if you have a planet on the top here, you have a core with a gas atmosphere, and you start losing mass, and once it gets to the top of this valley, it has only about 1% of its or less of its mass in gas, and it starts losing gas, and it can lose go over here to having no gas very quickly. So in other words, if you have a little bit of gas, you're very puffy, and if you have almost no gas, you're not puffy, and there's not a lot of mass in between. So you can get this gap either by photoevaporation, which is what I'm going to talk about. There's also another process people talk about called core powered escape. They work together. There's a lot of interesting stuff there that I'm not going to talk about today, but I'm happy to talk about with anyone who's interested. Photoevaporation, though, comes from heating the upper atmosphere due to UV or sometimes X-ray photoionization. So you bring in a photon, you ionize your hydrogen atom in this case, you kick off an electron that has an extra energy, it collides with its neighbors, heats the gas. So it's photoionization heating. This is mostly at optical depth about 1 for the UV. For the extreme UV, which is very high in the atmosphere, it's got 1 to 10 nanobars. That's because the cross section for photoionization is very large. So, while optical photons reach the surface of the planet, these ionizing photons are absorbed very high. This is true in Earth's atmosphere as well, in our thermosphere, which is at about 1,000 Kelvin up at height. In our atmosphere, what happens to that energy is it gets conducted down to the boundary that's mesosphere and radiated away by carbon dioxide, total nighttime emission. And so it doesn't lead to a big outflow. But if you're much closer to your star and you have a lot more energy, then you can get a classic Parker wind outflow. Just to remind you, this was developed for a stellar wind. It's actually a much clearer model for these planetary outflows because stellar winds are not collisional, planetary outflows are. But a Parker wind says that if we do the simple case, it's isothermal, you have a fluid that's collisional. Then if you try to make a hydrostatic atmosphere, your pressure at infinity is greater than zero, and that's bad because that means that you're being accelerated outward at that pressure. And so you end up with an outflow velocity and you're accelerated by this pressure at large distances. So if you have a confining pressure at large distance, you can prevent that from happening, but generally you're outflowing into close enough to a vacuum that doesn't happen. And the key thing here is that the energy for the PdV work needed for the outflow comes from the isothermal assumption. So in reality, you're actually being heated by something, and you have to be heated enough to drive this outflow, and photoionization heating is where this is coming from. And again, if you have enough of that heating, you'll remain collisional. You'll be a fluid outflow. You'll be collisionally coupled. If you don't have enough heating, then you won't, and you'll end up with something like the Earth's atmosphere, where you're still heated, but you lose mass by Jean's escape, the tail of the Maxwellian distribution, and whatever energy is left over, at least in Earth's atmosphere, is not by molecular light cooling. Okay, so this idea has been around for a while. It's been modeled by a lot of different people now, and there are a lot of models that have a variety of compositions, hydrogen, helium, a variety of different heavier metal compositions. But while the hydrogen helium case has been explored in some detail, how this works in more metal-rich atmospheres, there's still a fair amount of work to be done. And I just wanted to show this recent result led by Yayati Chachan, working with Jonathan Fortney. It's an update on a paper from Daniel Thorngren, and in this work, by doing interior modeling of warm Jupiters that have both radius and mass measurements, we're able to show that the metallicities, even at very high planetary masses, are well above solar. So this is
bulk metallicity, including the mass of the core.
That's correct. This is bulk metallicity. But notice that up here, this is 10 Jupiter masses. So the mass in the core is not a substantial fraction of the total metal mass that goes in here. So
that can be quite different from the atmospheric metallicity.
It absolutely can. So you're right in that we should be drawing a one-to-one correlation. But what this is saying is that even for the Jupiters, like this is one, the bulk metallicity is very high. And if you want to make, it's like 9% if you try to, do a best fit for this, including a core that's 15 or 20 Earth masses. Which is, as high as you probably want to put in, you may disagree. So this isn't mostly in the core unless you run a really massive core. Up at these, this is like hundreds of Earth masses up here.
What's the line?
Oh, this is a model that Yayati made that's basically a fixed core mass plus a atmosphere with a fixed metallicity enhancement. So he's trying to do a simple bit. And you can see that a model that simple does indeed match the data fine. That doesn't mean it's unique. Yeah. So we don't expect these things to be entirely hydrogen helium. And that can matter because metals, if they're included in the outflow, will contribute to line cooling. And they'll also, if there are enough of them, certainly at the low masses, they're going to change the mean molecular weight of your atmosphere. Yeah.
I guess this maybe is the point, but evidently in that model, we can identify what we expect the core mass to be over the population.
Yes.
Is that interesting? Is that like a...
Yeah, and it's about, twice what you might have expected. I don't know, if you expected something, yeah. So it is interesting. It is interesting. It's not clear whether the ones at the low masses are truly the core mass or whether there may be some collisional growth down there as well, because these are just planet masses, they're not truly core masses. So you can make a model, you can equivalently say you have 10 Earth masses in core mass and then say that you have collisional growth going on down here. There are many ways that you could model this, but the point here is that you don't need a particularly fancy model to fit it. Yeah.
So some of them have metallicities below solar. Are these the ones, kind of puffy Jupiters with very large, for which you basically need a negative mass of the core?
all of the
No,
ones
no, I
that
mean,
go
well,
below.
the dots, I mean, I'm not talking about the airbursts, like the one
Yeah.
that two Jupiter masses, I mean, it's pretty, yeah, this one.
I don't actually know off the top of my head which one this one is. That's interesting. I'll go look into it, but I would say when I look at this, I see the big error bars.
No, sure, I do too, but the ones closer, I mean, you do expect some core, so these ones look like they would require a core of negative mass. So this would be the ones, the puffed up Jupiters with very large radii.
So these, Yayati has attempted to remove all of the puffy ones. So this is warm Jupiters, not the hot Jupiters.
Well,
So it's, he's explicitly tried, and Daniel did that in the earlier sample, though Yayati has a much bigger sample now. Is explicitly attempting to take those out. So, so maybe that one should have been taken out and was, I don't know off the top of my head, but it's a good one. I'll look into that. Okay, yeah. So, okay, so we do need to consider compositions, and that, you know, becomes glaringly obvious, of course, as you go to lower mass things. I'll just let you know that one of my graduate students, Maddie Broom, who's graduating this year and applying for jobs, has put together a publicly available code. It's available now, called Windy, that can model these atomic outflows quickly, meaning in a couple of minutes per planet, including, you know, full spectrum and metal and metals for the atomic part of the outflow. So she's putting together some grids in this, and I don't have any headline results to show you yet, which is why this talk isn't about that. But this is available, and we're doing a lot of things with it. We've also been thinking in my group about molecules and how that's going to work for these photoionization outflows as you go to more metal-rich planets. And my former grad student, Renata Froelich, has put together a model that can do this. That can do this nicely. The currently published work is just for hydrogen, but you can see that when you put together a model that has the transition from molecular to atomic to an ionized outflow, you can keep track of what are the dominant coolants in each of these layers. Other people have done work like this as well, but the reason that we're building this model is to put in a coherent way molecules for heavier elements. And I just want you to look at the red line here. This is a heating cooling plot. This is the cooling zone in red for H3+, which is the dominant molecular coolant in a hydrogen dominated atmosphere. And you can see that for a hot Jupiter, it's really just the base. This is at 1 point, you can't read it, but it's at 1.03 planetary radii. So right near the surface, you can get molecules, but the whole rest of the thing is atomic. But if you make a sub-Neptune, the red line goes all the way out. And that's because the escape velocities from these smaller planets are much smaller. And, well, not much smaller, they're a little bit smaller. So you don't have to get quite as hot, and you don't always thermally destroy all of your molecules. And so in these smaller planets, you're going to be able to cool with molecular coolants much more effectively. And we do have some preliminary models showing that. And so I think that when we're looking at these lower mass planets, the current escape models that we're using at some point are going to just be entirely wrong, because we're going to be dumping a lot of that energy into molecular cooling the way we do in Earth's thermosphere instead of into the outflow. Okay, so that's some background, but I said that what I'm actually wanting to talk about in this arena is interactions with the stellar wind. So here's a movie of a planet. This is a hot Jupiter now, losing gas and interacting the stars over to the side with its stellar wind. Here the wind is weak, and you can see that the atmospheric gas is confined because it's turned by Coriolis forces as it leaves the planet. The outflow velocity from the planet is a lot smaller than the orbital velocity. So you have both a leading tail and a trailing tail coming from the planet. If you put in a medium strength stellar wind, you actually get this nice limit cycle here going on. And then for a strong wind, you have a nice confined tail that looks like a cometary tail, but it's being confined by the stellar wind.
So, can you remind us, please? So I remember a few years ago, I talked to James, I talked to David Singh, who had a postdoc who was working on the actual observational constraints.
Yeah.
on outflows. So I remember that there was some data on the actual, like, okay, let's detect these outflows in action.
Yeah.
And it was very controversial, and I don't remember what the end of the story was, so I was wondering if you can update us.
Yeah, so there are two, well, there are three ways that people have looked at these outflows, and both of them will come up in a minute in the top, and two of them will come up in a minute in the top. So, well, I guess all three. One of them is in Lyman alpha.
Yeah.
In Lyman alpha, the ISM absorbs the center of the Lyman alpha line. So you are restricted to seeing material at large distances from the planet. I'll show you a diagram in a minute, because most of the outflow is actually unfortunately absorbed by the interstellar medium. So it's hard to look at the main outflow. There's helium,
That's the one.
helium triplet. The helium triplet is a transition that you have to populate by a recombination cascade. There are a bunch of beautiful helium absorption measurements, and I actually saw one. I haven't had a chance to read it yet because I just saw it yesterday as I was traveling on the archive, showing that they're seeing helium around half an orbital period. So anyway, I look forward to reading that.
It's a big stretch, so it populates kind of the orbits. And you continue seeing it even after the planet has gone away from the line of sight.
That's the implication, yes. And that is very nice. You can see it from the ground because the helium triplet is in the optical, but
It's the roughly 1 micron long.
it's the 1083.
Yes.
Yeah. And well, I guess it's not the optical, then it's in the near infrared, but you can do it from the ground, and there have been a lot of these measurements. You can't get direct mass loss rates from them because you have to understand the population of the line. So it has its own issues, but it's very nice. Oops, sorry. And then there are some tentative metal line absorption detections, but those, as far as I know, are still not quite 3 sigma. But there are some lower in the atmosphere absorption measurements that are sort of like where it's not clear whether they're actually part of the wind region.
Do you remember which lines?
The lower down ones.
The metal ones. Sodium.
There are sodium absorption measurements, but those are generally thought to come from lower down. I know, like oxygen and carbon. Magnesium. I have to go back and look. I don't have that.
I'll ask you for
ask me.
references later. Yeah, thank you. Yeah.
Yeah, but they're not 3 sigma. But there's, the question about the metal lines is that this wind is launched from, nanobars, 10 nanobar pressures. So if you get the metals up to those pressures, they'll go with the wind for sure, and they should absolutely be there. But that depends on the turbulence strength in the atmosphere, whether you get them up there. So they might be there, they might not. Probably they are, but it does depend on the atmospheric turbulence. Okay, so just picking the Lyman alpha of those 3. If you look down here, so this is the orange dotted line here is what the Lyman alpha line looks like from a star. This is a schematic when there's nothing coming in front of it. And you can see that there's this big dip in the middle because of the ISM absorption in the middle region. And also notice that big dip extends out to, say 50 kilometers per second. The outflow from the planet should be going at about 10 kilometers per second. The way to think about that is that's the sound speed at 10 to the 4 Kelvin. So it goes supersonic, and you can't really get above 10 to the 4 Kelvin because just like in H2 regions, you'll dump your energy into either hydrogen Lyman alpha line cooling or metal line. So you're not actually seeing the main outflow, but when that material comes off of the planet, then it either, so in this diagram, it's being confined by the stellar wind into a tail. It can be going in either direction. If you have weak stellar wind, then there's still material around that could conceivably be producing absorption at these large offsets. And indeed, it is observed at like 100 kilometer per second offsets. The orbital velocity, there's plenty of orbital velocity around for that to work. But if you're looking through this outflow, if I just draw this picture like this, we're looking through the outflow as it's going by us. And so you don't get to see much of the orbital velocity. Unless this wind outflow is being radially accelerated by the stellar wind. And remember, this is a collisional outflow. So you're being pushed on its surface. You push this thing outward. And if you go back and look at the right-hand picture here, you see that this is, settles into a tail that is not going exactly in the theta direction. It's being pushed outward. And so you have some accelerated velocity in the direction of the observer that's going to increase over time. But you're also going to be ionizing this outflow over time. So as you go, you have increasing ionization fraction. That's only the neutrals you can see.
Where is the Alfvén compared to the orbital radius?
It's the sonic point or the Alfvén point is like
Well,
right.
no, I mean for the stellar wave.
We don't know. It's
For
similar.
the sun, it's something like 12, 20, I think, polar radii.
Yeah, so it's
That's a
similar.
slow, okay.
Yeah, it's similar is the point. Like it could be, because these are like, 10 stellar radii, 0.05 AU ish. So it's right about where you would expect it to be. And so it depends on the star. So I've drawn this as if it's outside the Alfvén radius. But if it's inside, then this is.
I'm just wondering if it's ever possible for the material, instead of being blown out, to actually lose angular momentum because let it fall onto the surface, then we would see high velocity.
It's definitely possible, but that velocity would be in that direction instead of this in its direction toward us that we're seeing in these examples that we have. But theoretically, it's certainly possible. And people have looked for these, as I said, these show velocities in the direction toward us, not the direction away from us. People have looked for signals sort of, similar to the magnetic spots on Jupiter from Io for exoplanet, and there aren't clear indications of that. But if you just ask theoretically, sure, I don't see a reason why you couldn't. And stellar wind strengths are very ill constrained in general around most stars. I mean, we have some astrosphere measurements of them, but for the most part, I think you have a lot of room to say that should be happening. The reason I'm focusing on this is because of this observed velocity coming toward us. So you're pushing this gas. It could also be radiation pressure. It doesn't have to be stellar wind. If it's radiation pressure, it will still be a surface force. It's just a matter of for your particular star, which of those is stronger. And the idea here is that if you say you have a certain amount of length to this tail that you can see in absorption before it gets ionized and becomes transparent to your Lyman alpha photons. And over that length, how much can it be accelerated by stellar wind or radiation pressure, if you prefer? And that tells you, over the length of your orbit, where you can see this this absorption at larger velocities. So we've been able to look at the current detections and non-detections, and this sort of model will match all of them. But there isn't a lot of data that follows these transits over a large fraction of their orbital period. Most of the data is sort of, right before transit and then, right in transit. And there isn't a whole lot that will follow over a long period. And in fact, if you're a hot Jupiter, these models show that often you won't expect to see absorption during the transit itself. And you have to wait a while until you get accelerated enough. And if you just waited a long time, you might start to absorb later. And we don't have the data set to show that, whether that's true or not at this point. For Jupiter's for the most massive planets, even out here where you come into ionization equilibrium, if you were accelerated into the right velocity range, you would still be able to see the absorption. For lower mass clumps, that's not true. So anyway, we've put together these observations can be difficult to interpret because again, they're not coming from the main outflow. They're coming from large scale interactions with the environment. But as I said, this framework for understanding when you should and shouldn't see these transits, it's at least consistent with what data there is now. And there's a currently ongoing fairly large HST program called Stella that's led by Perkwood and Shreyas Visapragada, and they are looking for their Lyman alpha transits on longer baselines across a large stellar sample. And so the hope is that we can confirm this model framework and have a stronger hold on how to interpret these observations. I mean, a lot of times people will cite these Lyman alpha transit observations or the helium ones and say that they've measured a mass loss rate from a planet, and it's all model dependent, but you just can't do that. So, so we really need the observational confirmation. Okay, so that's where we are on the Lyman alpha transits.
How do you treat the thermodynamics of this flow? There is a shock heating, there is a photoionization heating, there is also cooling. Is this all included in these simulations?
So the simulation includes the photoionization heating, Lyman alpha radiated cooling. It's only these simulations are only hydrogen. There are people who have done similar simulations that include more species. This model that we made, and Ethan Schreier has put it together into a nice version that can be used to fit data because it uses essentially an equivalent of geostrophic balance to get the shape of this tail, which matches the simulations. But in terms of the heating and cooling, to do these fits, you don't actually need to know because you just care about the velocity along the tail.
What about the vertical height?
Oh, you do need to know the vertical height, that's right.
That's
So the vertical height and the tail, but you can fit those using the data. So so from an observational perspective, it's a fit. From a theoretical perspective, we do have these simulations do include photoionization heating, and they include radiated cooling. So they're done
with these observational feats.
Sorry, what?
You can then compare them with observational feats and see how good they are, right?
Right, and Ethan's model, matches these simulations well, but I would say like that's by letting there be free parameters. But it doesn't. He has compared against the numerical simulations, and they do match.
So does one see this line up WASP 12 is one system I spent some time with, that's an F star. You see it in systems that you don't think have much of a surface convection zone.
So WASP 12, the planet may be Roche lobe overflowing, so it's like a very extreme outflow. For a while until recently, it was stated there is no helium transit. It's not what you asked, but that's what I'm remembering off the top of my head. And recently, I think that there's been a new result showing that maybe there is a helium transit at a later epoch. In terms of Lyman alpha, I don't think there's a Lyman alpha.
Yeah, I just remember, but you said as you go to the earlier spectral types.
Yeah.
It's you think there's still a wind pushing on the outflow?
That's a great question. So if you go to A stars, you would think you'd have a much stronger. Most of these observations are not around the earlier stellar types.
Yeah.
The helium observations are prefer K stars. Most of the Lyman alpha ones are G stars, though they're not all.
So that would alter the kinematics of the tail primarily, is that the?
It would alter the kinematics of the tail.
Yeah.
Yeah, no, that's a great point, and I don't,
Stellar type, yeah.
I'm gonna look, that's a great point, but. I don't think that there certainly aren't a lot of observations, but I'm gonna look into that, that's a great point. Okay, yeah, okay. But, what if you don't have a strong wind pushing this out to that point? And in fact, then in principle, you can accumulate this material into a torus. And people do actually, WASP-12 is one of the systems that has motivated this thinking, which is consistent with what you were saying. So you'll accumulate material into a torus if you have a weak stellar wind. And can we look for that? So WASP-12b has an anomalously low log RHK. And that has been interpreted as being from circumstellar gas absorbing in the calcium, became lowercase i's, but line H and K line cores. And it's also been quoted that about a third of stars with close in planets has an anomalously low log RHK. So
what is this log RHK?
yeah, let me direct you right here. So what this is, these are, so calcium, so the log R prime HK are stellar activity measures. These are stellar lines that are interpreted to be associated with stellar activity. So if you're looking for a transit, you can look in time, right? And you can say, I'm absorbed and I'm not absorbed and then I'm absorbed. So you can just compare out of transit and in transit. But if you're looking for a torus, then you don't get to have that time change. And so you have to actually know what the star is emitting in your line that you're looking to absorb. And that actually varies depending on the activity of your star. And so here on this x-axis, this is log R prime HK, and the gray arrow says that you go to the right on this plot if you have increasing stellar activity. What this is, it's a measure of, this is the solar calcium 2 K line, and it's actually a big fat line like that. But it has this line core right in the middle that goes up. And if you're more active, then it's taller than the line core. So, so that's just about the star. It's not about the planet at all. So if you say, okay, well, you look at this line and it has a weaker line core, and, it's just not a weaker, a less active star. Well, you don't. But what Ethan Schreier, who's a postdoc in my group right now, pointed out is that helium lines, we know, are good for absorbing, this gas. This gas is good at absorbing in the helium 1083 lines that we were talking about before. And here's a picture of the helium line. It's a triplet, but there are two peaks because two of them are blended in this. And what's nice about this is that the dark lines here are what you would, if you start with the dark lines, so the calcium core, or this helium absorption triplet, and then you add in some gas, you're going to reduce the core of the calcium. You're going to make the helium line stronger. If you look at these black dots here, which are from a paper by Graham Smith a while ago, this is an observed correlation with activity between the strength of the these calcium lines, and log R prime HK is a non-trivial, messing around with that, but just think about it as it's just reducing this. I have your permission.
It's great. Love it.
Yeah. And here's the equivalent with the helium absorption. So with increasing activity, you go up into the right on this plot. But absorption by circumstellar gas takes you this way on the plot. So the hope is that if you put enough gas in front of this, of a star, you'll be off of the correlation in a way that can be observed. And so this is inspired by these previously reported results. And so Ethan's made a model of tori produced by these planets. You know, essentially you can very quickly lose enough gas that the torus will be optically thick to the ionizing radiation that drives the outflow. And sort of, you know, the geometry of that still needs more work to figure out, but you can imagine, you know, turning off the atmospheric loss if you build up a big enough torus. So that's how he set his torus density. It doesn't take very long to lose enough gas to do that from a hot Jupiter. And these colored points here around K, G, and F stars are the what you'd expect on this. So here, if you're wondering about the axes, they look better here, long arc HK and the helium. And you can see that they're very well separated. Yeah.
Why does increased activity lead to reduced helium-1 absorption? Is that because it's ionizing more helium?
It's more absorption, but more absorption is deeper.
No, more deeper is a larger equivalent width, though.
Yeah, more equivalent with.
No, but I was asking about increasing activity, so it's the other way around.
Oh, increasing activity.
Deeper absorption. That's my question.
Increasing activity means just stronger absorption.
Oh. It just goes the other way for the HK. Okay, thank you.
It just goes the other way for the HK. Yes. It's because we're looking at this line core versus like.
Makes sense.
So anyway, they're off the correlation, and that's essentially the result. So we'd like to go look for this. And what's nice is that you know, you can look for this across a population of stars. You don't need to be looking at transiting planet systems. So that's what we're trying to go after next. And you know, you do need a substantial outflow from planets to overwhelm the stellar wind, or you need a weak stellar wind. So maybe, as Jeremy was saying, that will mean we'll be looking at, you know, higher mass stars to look for this. The constraints on the stellar wind distributions for these things are very broad, but the stellar wind strength that you need to overwhelm the planet mass is smack in the middle of the current constraints. So we don't know if these tori are going to be out there, but I think that we'll learn a lot about stellar winds in addition to about planetary gas if we do or don't, frankly, find them. Okay. And I'll just end this part by also noting that though that measurement has nothing to do with the transit of a planet, these tori can also affect the transit spectrum in helium. And I mentioned earlier the WASP-12 system. There's now disagreement about whether there is an observed transit in helium, but it's kind of interesting the way this works, right? If you start with no circumstellar gas is the yellow line. So you've got, this is phase normalized flux. So this is just the transit in the helium line, the depth of it overall. We see that double peak here in the with wavelength in the line. As you add some circumstellar gas to the red line, it makes the transit a little weaker. It's not because it blocks less light, it's just because it was always blocking some of the light. And then, so you can see the double peak is a little weaker. And then if you make there be even more gas, it's blocking even more of the light all the time. And then you get this like weird purple structure here. So now it's absorbing, you're not seeing your peak absorption in the line. You're seeing your peak absorption in sort of like the edges where it's more optically thin. because it's completely absorbed all the time in the lens centers. So, so this is another thing that you can go look for transiting systems like Westpole. Okay. All right. I'm going to move on, but are any last questions about this?
So in this torides, I mean, as they build up, do you expect to see any signature of like double emission lines? You know, are there any emission lines that we produce there strong enough? Because if you're not remove, I mean, if the wind is not strong enough to kind of kick this stuff out of the system, it will just keep building up. I mean, you have a source of mass, and you will be feeding the decretion disk in this case.
Well, you might be feeding you said a decretion disk?
Yeah.
So when we did this modeling, we assumed that you won't keep building it up because at a certain point, you'll build up so much between the planet and the star that you block the ionizing radiation that's actually driving the planetary outflow. So we did put a limit on the amount of material that you could build up. There are other absorption lines that are probably observable. We just were focusing on these two because they have this nice, you know, they're well known and they have this nice opposite behavior. I don't think that there are any emission lines that are going to be strong if you believe that assumption that you will shut off your mass loss when you become optically thick to the ionizing radiation. But it isn't clear whether you just have a torus on both sides, whether it accretes, whether it is, you know, being pushed out.
It would be a symmetric.
Yeah.
Some hole on the inner side and you know, just
Totally.
really expanding.
Yeah, there's gonna be some pretty interesting geometry, and so if you end up and you know, we have not worked all of that out, other than to just say it could be a bunch of different things, you know, but if you don't stop the buildup of material, then yes, maybe you can
What is
get
envelope from planet?
that 10 to the 11 grams per second.
10 to the okay.
I would say 10 to the 10 is the number I have in my head for a typical hot Jupiter, but these ones that are outweighing their stellar winds tend to be the stronger ones in this particular model. So in this model, we're not getting emission lines because we're assuming that once you've lost enough mass, you're sort of like living, there's some going to end up being some material between you and the star that will cut off the further loss of material, and then maybe it will accrete, and then you'll like
I mean,
lose
there
more.
should be a steady state, right? I mean, if
There'll be
you're
a
cutting
steady
off the
Yeah.
folding stuff.
But it won't necessarily indefinitely cut off the loss of material, but it will limit the amount of material that you can
Yes.
build up at one time. And so and with respect to your question, that's a conservative assumption. And under that conservative assumption, I don't think there are going to be visible emission lines, but if you want to relax that, then there. All right. We are being chatty, which is excellent. So I'm only going to talk about one more thing. All right. So, okay. So what else can be affected by stellar winds? So those outflows, they're fluid outflows. And so I said, you know, the stellar wind impinges on them as a surface force, same with radiation pressure. But if you have a much more diffuse environment, then you know, either your stellar wind and or radiation pressure can affect small particles on a particle by particle basis. And, you know, and in particular, small dust can be affected. And the standard way of parameterizing this is with the parameter beta, which is the force from radiation, or stellar wind by the force of gravity. And so I'm going to tell you about some work that Arcelia Ruiz, who recently graduated from my group and is now at postdoc in Exeter, did on the AUMIC debris disk system, trying to explain some fun observational puffs that have been coming out of the disk. These observations have been around for a while. You might have heard of them, but I'm going to review them now. So this is from 2015 from Boccoletti et al. This is an edge-on debris disk system, AUMIC. Here's the midplane of the disk. You can see these two sort of clouds on top, and this is scattered light image. This one's from Sphere. And you can see over time, that the locations of those clouds are moving. I'll do that one more time. So now they're in the circle, now they're moving out of the circle. So that's fun. Just because I'm gonna refer to multiple different of these clouds later, I just want to show this example of what is identified by the observers as the cloud. So there's two ones that we saw that are, well defined. There's this one that looks like a little arch. Notice that, and then there are these that I don't know if I would have been able to identify those as blobs. They're kind of like big
What's
spread
the
out.
angular linear scale?
Oh, I have that.
I mean, is it a distance where the orbital time is very long or?
Oh, this is
Order of Saturn's orbit.
yeah.
The previous plot showed Saturn's orbit.
Oh,
Oh, yeah, there it is. Saturn's orbit. Thank you.
okay. Okay.
Yeah.
Yes.
So it's, it's closer in than some disk images than you're used to, but it's not really close in. Yeah,
Do we have estimates of the line of sight velocity?
yeah, I'll get to that. Okay, there are some blobs on the other side. I'm not gonna talk about them today. Okay, so, but they're not nearly as clear. So they're these blobs moving on one side, and they're not doing the same thing on the other side. It's not symmetric. Okay, so what can produce a periodic clouds of dust on one side of the disk moving outward at high speeds?
On one side, sorry, you mean left versus right?
Left versus right from the line, yeah. So this is stars, the stars right here.
Yeah.
I didn't show this side. There are not equivalent structures on that side.
But also, are they always?
They're above.
Vertically on one side? You don't see them on, are they always vertically on one side of the disk?
Yes.
As well? Okay.
I mean, this is it. This is what this is kind of, I guess I haven't shown every single epic, but that's kind of what we got. Yeah. And then, but it's not on the other
This
stars.
is the only system that we see this.
This is the only system that we see this, but that doesn't necessarily mean that if we saw the same process from a different viewing angle, there would be others. Yeah, this is a very edge-on system. This is the only system we see.
Data Pig is another super edge-on system.
Yeah, and it has a warp in it that's known to come from a planet, from secular interactions with planetary orbit. But it doesn't have this sort of thing where blobs are moving out. Yeah.
In terms of timescales, are they about 10 years apart?
So June 2016, May 2017, so those are a year apart.
Like if I were,
May 2015, so these are about a year apart.
but if I were to push them all the way back to the star, would they intersect with the star?
Yeah.
On the other way?
Okay. So, people have looked at this, and tried modeling it either as localized dust avalanches or a giant collision in one part of the disk, with then these blobs coming out, because they have a high beta. In this system, it's almost certainly stellar wind, rather than radiation pressure, because this is an M star.
The radial velocities are like 10 kilometers per second, 20. Okay, oh, 5, 10, okay.
There's the velocities, that's the answer. Yes.
Roughly how much grain mass? Is this far more than you could get out of a big comet or something?
It is not a large amount of mass. Having a collision of some comets, like a big, you can't get one comet to do this, but you could have, a collision of, you don't need a ton of mass. If you could get a comet to do it, it's, these localized dust avalanche models involve, a collision between, sort of like a Kuiper belt object kind of equivalent, which is what you're getting at, and then it generates a bunch of dust. But then the problem is you have to keep doing it every orbital time because you need to have more and more blobs.
Well, I was reminded by Nadia's mentioning beta pic. There are comets apparently, ones you
Yeah.
beta pic all the time, you see them spectroscopically, right?
Yeah, I mean, this is a debris disk. There are certainly, comet bodies around That these things are moving away from the star, yeah. So if you can make it work, I think that the mass isn't necessarily. Okay, so anyway, you can match this, starting them in the same place. People have also tried having it be maybe like a planet with a circumplanetary ring that is moving around and keeps being interacting with the stellar wind. I'm going to be focusing on this kind of model. So we're thinking if you have a model like this, it does a reasonable job of fitting the data. So you're every once in a while, every orbital period, you're making some dust. You're pushing it outward with your stellar wind. But giant collision, localized dust avalanches, is there a way that we could get that in what felt to us like a more natural way? Yeah.
With the movie, we see that outwards motion. Is it clear that that's not a projection effect?
Oh, it's definitely a projection effect.
Definitely.
I mean, well, it's
Because
going out, but there's definitely projection effects going on.
Because if it's, not a, 90-degree phase, then.
Yeah.
And it's coming towards you, they will appear to move out. Just from the projection effect, right?
Correct. But they are going, here is this dotted line is the escape velocity.
Okay.
So here, it could just be that, but then once you get out here, they're actually going faster than the escape velocity. But they're definitely being projected, right? So if you take position and speed, here are those 5 blobs that I've highlighted. And the velocities are calculated, or the projected speeds are calculated by doing the 2 epoch positions and dividing the amount of time.
Okay, sorry, so just to clarify, so the fact that there are 2 different blobs, you're saying, okay, this is a planet orbital period that bumps things into this, so like using your cartoon, the reason that there are 2 different blobs is that it's the orbital period that we're looking at.
So I haven't said why I'm saying there are different blobs. That is going to be along the lines, but I haven't actually said yet.
Okay.
Yeah. Okay. So we got these 5 blobs. If you fit these curves on here are essentially hyperbolic orbits with some beta that appear. This is from Silvestri et al. In 2017. These are the beta 10. They've started them at very different radii. And the reason you can do that is because of the projection effects we were talking about. You can put it at different phases, different projection. Okay, so what we're suggesting is that you can get, I guess some inspiration from the beta pic kind of system where we know that planets on inclined orbits are producing a warp in that system. If you put a giant planet on an inclined and eccentric orbit, in the system, with reasonable parameters that are consistent with the kinds of planets that we expect to see, and you have your debris disk, then you can just pick some of that dust up every orbital period. And now it's not in the plane anymore. And so now we see it being pushed out as glob. And the material that's in the plane, either you're shielded by the other stuff from the stellar wind, or you're just being pushed out all the time, but it's just all in the same plane. So we don't see it as anything different from the plane. And so you push them up and the stellar wind pushes them out. So that's the argument. And so then the planet period in this case must set the time between cloud ejections, which is about 7 to 10 years. So you know where you have to put your planet. And it kicks more at apocenter than it does at pericenter, so you can get a one-sided thing. Yeah.
So if I wanted to play devil's advocate.
Yep.
Recognize it in those images, it is quite disjointed, like those blobs.
Yeah.
Is that a problem with this?
So why don't I show some movies of the simulation and you can give your opinion. I'm starting, let me just show the movie, click, 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 click. We found some parameters, doing a thing. Okay. So here's a top-down view, just so you can see what's going on. I'll just Here's the planets in the middle. It's pushing out blobs. All right. And then here's an edge-on view. And find a nice place to. And maybe I'll just pause it right there. Look at that like arch. I think that arch looks kind of like the arch. So I'm out of time. So I'm just gonna end on that. Yeah.
Yeah, you say star and still win. But when you define beta, you point out that the force on these bands could be either radiation pressure or wind pressure.
Yeah.
If one, does one have more than one band and scatter? I mean, can you get some idea of what the particle size is? Maybe looking at two different bands and then you know the luminosity of stars, so you can look at what the beta should be. Radiation pressure level.
Yeah, so there's more to do in that area, but I will say that there are measurements of the scale height of the disk and ALMA bands as well as the scattered light images. The ALMA ones are actually
Millimeter size.
yeah, anyway, those don't see this, but you wouldn't expect them to because they're too big to be pushed out. Yeah.
It makes a big difference whether there's a 1 micron or 10 micron as far as.
Right, no, I totally agree with you. So this, do I have it on here? The beta here that we're using for this simulation is something like 2. So not 10 like that other one. So you can get the basic behavior for a whole range of betas if you pick other properties. This particular simulation, our fit was 2, but I agree with you, and we just haven't done it yet. We're trying to figure out what other.
Because in comets in the solar system, you see 2 tails, and there's an ionized tail, which is really because of the magnetic field in the solar wind.
Yeah.
And then there's a dust tail, which is at a different angle, and that's radiation pressure.
Yeah, I mean,
And so I'm just asking, which is it in this case?
people who know about this M star say it's definitely the stellar wind, but the easily available observations are just these scattered light images that don't have a clear particle size dependence, and then the larger ones where this doesn't happen and you wouldn't expect it to. But I agree with you, and that's a direction that we're trying to look into more.
Okay, first we'll thank Ruth and then go on to the questions. Okay, now more questions. Yes.
So the only ingredient to answer George's question, I think the key ingredient is eccentricity, right? Like if it was a circular orbit, then you wouldn't see those puffs, right?
You also need the inclination to bring it above the plane. You can do it with just inclination. It's just then you have to ask why it's only on one side.
Right.
And like, it's easier to do that. You can play around sort of with your orientation and your viewing angle, and you can get like things coming off of both sides and maybe get it like behind your line of sight. So there's not like a single set of planetary parameters that will do this. There's sort of things that you can play with, but the main thing you need is inclination. But again, like the beta pick system has that planet incline.
And that's what I wanted to ask about. There seems to be some symmetry in your simulation.
Yeah.
In terms of material coming off both sides. You could even see in the edge-on view that there was a weaker feature going the other direction.
Yeah.
Above, in this case, below the plane. What causes the asymmetry in that one of these is so much more luminous?
So 2 things. One is the eccentricity. So like one of the sets of puffs is launched near well, it's not actually, it takes a little time for it to be launched, but like from the epicenter interaction. So that's closer. And then the other thing is we just played around with the orientation to make it so that the ones that are leaving the other way are obscured by the disk. There are actually some observations of something on the other side. So there isn't nothing on the other side. It's just less clear. So I think that sort of the orientation may just be the.
So
Question from.
in these simulations, do you assume that the wind is not active in the equatorial plane, or how do you avoid this problem of You have this reservoir of mass, right?
Yeah, great
Why do you
question.
need to raise it up?
Great question. No, in the simulation, we just say like you have to be a certain height before you start
Ah,
getting
okay,
pushed
so
out.
But
Yeah.
like in reality, wow, what do you think about, wow?
Well, you're
why
constantly
you
making, I
rest-
mean, this is a debris disk, you have to be constantly making these small particles from collisions anyway. And so you could just be being pushed out in the midplane.
Well, you know the time on which you're losing them, so that must be a pretty efficient producer of.
Well, that's true of any debris disk always, because they're always being pushed out by radiation pressure or stellar wind. Like, that's the whole reason that we know that these things are young. Or that's not true. That's the whole reason we know that these things are generated by Kuiper belts equivalents.
Cool, we'll keep talking. Later.